As always, our recordings of our virtual meetups will be available on YouTube about a week after the meetup, and we'll post a message on Meetup when the recording is ready. I am very pleased to introduce our speaker today. Dr. Stefan Gary is a physical oceanographer and climate scientist with 15 years of experience observing and modeling the North Atlantic Ocean. In his current role at Parallel Works, Stefan works with platform users to develop workflows in Parsl and other frameworks for earth and environmental science applications, including machine learning. He has also taught undergraduates and graduate students in the US and in Scotland. Today, you could ask questions at any time. You can use the chat, or you can use the raise hand feature in Zoom, or you're welcome to unmute yourself. If you do any of the former two, I'll interrupt our speaker with your question. So feel free to ask at any time, and I'll pass it to him.
Great. Well, Rebecca, thank you very much for that introduction. Hello, everybody. I'm going to switch over to screen sharing. Okay, there we go. And great. And yeah, so I'm really excited about presenting this talk because as Rebecca noted, I'm an oceanographer, but I'm also sort of within the last year, I started full-time at Parallel Works and went from sort of an academic track into industry. And I've really been enjoying working with scientists, listening to what they have to say and saying, oh, I know how to find a solution for that. And so hopefully this is some opportunities to see some solutions. So we're going to talk about Python-based machine learning and high-performance computing workflows. And this is in collaboration with my principally 4 other colleagues at Parallel Works. And so that's Alvaro Vidal Torreira, Michael Wilde, and Matthew Shaxted. And I put my contact information down at the bottom of the slide.
We already have a question. Anna asks,
Great.
Is Michael Wilde from Argonne?
Yeah, he was, well, he's on, I don't know if he's still affiliated or on leave, but at one point he was there, yes. And so, okay, so I will switch to the next. So here's a brief outline. I'd like to start with a motivation, a challenge, and some definitions so that we're all on the same page. And then I'd like to present a solution to this challenge, and that is Parsl, the Parsl parallel scripting library for use in Python. And then I'm going to go through sort of 3 examples or use cases of Parsl. We'll start with a simple Jupyter notebook that sends jobs to the cloud. And the take-home point there is that Parsl code can be used to broadcast a calculation. The second example will be some recent work using scikit-learn and Parsl, and some lessons learned there. Then we'll look a little bit at an idea for using sort of integrating a workflow with machine learning, integrating machine learning and a large-scale CFD, so that'd be computational fluid dynamics app, into a workflow as sort of a potential building on the previous example. And then I've got some ideas for the future. Some things that are currently some new functionality that's currently being worked on, including things like clusters in the cloud and mixing and matching resources to better match the computational task. And so I wanted to start with some motivation, and that is, global innovation is driven by modeling and simulation, and that there are many applications that are in our everyday lives that are at one point were modeled by a supercomputer, and these apps that are running within the supercomputer are often they're codes that have been built up over the course of many years through scientific experience, and so they are well established, but also very general. They can be used for many different things. So, for example, a computational fluid dynamics code may be used to simulate an airplane, could be completely reconfigured to simulate flow in a city. And so there's a lot of the simulation has a direct impact in our everyday lives. And what I wanted to do was to draw on focus on some real world case studies to think about what these apps are like and how we can interact with these really large, potentially complicated programs, and how we can streamline them to make them easier to use. And so what I'd like to focus on is a little bit of sort of an example from weather forecasting, ocean currents, moving stuff, river ecosystems, and then a last idea about industrial design optimization. So these are the specific things that I can speak to today. And to sort of think about the challenge, so I mentioned these apps are whether it is a computational fluid dynamics code or a chemistry, a molecule simulator, or a weather forecast model, users often approach these codes with some trepidation in the sense that they can appear like the tiger on the left side, which is scary. Lots can go wrong. It needs huge resources to run, and so it can be sort of a very daunting task. But the point that I want to make is that it's much more manageable if you provide it with 4 things. These 4 key things would be, and so it becomes something more like a kitten on the right side, where this analogy would be like talking about providing shelter, food, love, and a laser pointer, right? So the idea is to ensure that you have computational resources to house that app. You've got data to feed it. You have a configuration, which is setting it up in the right way. And then a laser pointer is telling it when to launch, when to go. And so more specifically, there we go. To make sort of concrete examples for what I mean by compute resources. So for starting the compute resources, we might go to the cloud and use G-Cloud to create a compute instance. For data on that compute instance, we might mount an NFS file system, or we might copy over files from a cloud bucket using gsutil. For a configuration, that would usually be a configuration file that would include app-specific parameterizations, like the grid over which the numerical weather model is run, or the type of physics package that is used to simulate the clouds in the model. And the last part would be the launch, would be the exact command that is used to invoke and to run that app. So in this, if it's a containerized app, if it's in Docker, then it would be, for example, Docker run the application. Now, this is nice. What we really want to do, though, is take it even one step further, which is, even for numerical weather models, running one model isn't enough. We need to run an ensemble of models that are all started with different initial conditions, so we can understand, for example, the sensitivity to initial conditions. And so we end up with a situation that looks like this, where we don't just have one kitten, we don't just have one contained application. We are really trying to manage a whole flock of simultaneous simulations that are running together. Because this occurs for weather forecasting, but it also occurs for many other apps, because it's important to determine the sensitivity of the application to a range of parameters that it could be running under, to better understand what the simulation results are going to be. So, the idea is to, and so it's essential that we coordinate things, right? So I bet you weren't expecting to come to a talk where I was going to say that herding kittens is possible, but it is. And so now we're going to dive into the specifics of how we can do this and how we can manage all this and keep everything all coordinated. And so this coordination process or orchestration process is a workflow. And the workflow is used in many different contexts in many different ways. And so I wanted to put it here to describe exactly what I mean by a workflow in this context. The slide is divided into two zones. The top row would be considered consistent with what I would call persistent resources. So that would be your local computer. That could be the laptop that's sitting in front of you. It could be a login node on a Slurm cluster, or it could be, for example, if you're on the a user container that's on the ParallelWorks platform, which we'll see for a demo in a moment. The other persistent resource would be your storage. So like it could be a cloud bucket or a file system on a cluster. It could even be something on your local computer as well. And the last key thing would be an image or a container registry. So this is where you're going to be housing the source code, or the bulk of the model would be in these locations. Now, not every app is going to use each one of these different things, but these are things that a large app will often touch on. So in our case, for a weather forecast model, it's going to pull from each one of these different things. So the order at which then the bottom part of the slide are what I would classify as sort of temporary resources. So this would be the worker nodes that are actually going to go through the process of running the calculation. And they get spun up right before the job is needed. So that would be step one, where they get started. Then the config, the setup, and the launch. So that would be the love and the food and the laser pointer for the kitten would then get SSH. Those would be, say, usually they can be up to 3 or more separate files that would get sent to the worker node. The third step would be to mount or to copy data to the worker node that it would use. And then the fourth step would be to copy an image or a container there for to be run on the worker node. Once those pieces are in place, then the simulation can be started. The output is generated on the worker node, and then it gets sent back up into that persistent space. Whether it goes to the cloud storage or whether it goes to your local computer, that's up to the author to choose. Now, this is fine. As I mentioned earlier, we're going from not just one kitten, but we're really interested in maybe potentially 2 apps, stringing one application one after the next. So I put these pipes going into the top of the second worker node to indicate that it too is going to be pulling from your local computer, from the storage, and from the container or the image registry. And so on. You could even chain more of them down the line, and that would make for a progressively more complicated workflow. But these same steps would apply. The other dimension that we can add to this is to think about running not just one single instance of a workflow where you're going from app 1 to app 2 and so on, but there's actually going to be multiple instances running at the same time. So in the case of the weather forecast model, the app 1 would be to create the forecast. The second app would be to run post-processing. The third app might be to do some machine learning on that, and finally send its output. So how do we orchestrate all this? And what I'd like to propose today is and describe in some and also demonstrate is using the Parsl parallel scripting package, which is it's written in Python. It's for Python, and it's written by the Parsl project team. You can install it with pip install Parsl. It's also available for Conda. This slide is divided into 2 parts where there's some example code on the right and some information on the left. I'd really like you to focus on the information on the left first. And there, the really beautiful thing about Parsl is that there's two kinds of apps in Parsl. Parsl will either create what it's called, a Python app with the Python app decorator that you can see on the right side near the top. And there's also a bash app, which is all created with a separate bash app decorator. And Python apps we'll call Python functions. Bash apps can be used to call external applications. So you can have it run a shell command, or you can have it run, you can tell it to Docker run something, or any executable that you have access to in a normal shell, you can run with a bash app. Now, we're launching, the examples here are super simple. They're tiny little things that run very, very quickly. What we really want to do is replace the hello world line there with run weather forecast model. And what happens is it can take hours to run these large simulations. And so what these apps return are futures. They are Python objects that represent the result when it is realized. And so in your code, you can keep pinging that object that's returned from the function and say, are you ready yet? Are you ready yet? Or you can even halt execution and wait for it. Execution will wait until a certain future is ready, and then it can proceed. Now, if you don't ask for the future to realize itself, each app just basically gets pushed and it runs. And you can run multiple apps concurrently. And so the idea is that this allows for parallelization, because you could write a for loop around one of these decorated apps, and each instance will then just be pushed out to run, and they'll run in parallel. And then when you ask for their futures, you're then asking for all of them to finish, or you're asking the execution to wait until everything is finished. And because they're in Python, it's very, very flexible, and it really does work with write once, run anywhere approach. So how would we? The previous slide showed an individual app, and they didn't show how they can be chained together, which is one of the key challenges that was described in the previous schematics. And so the next two slides are going to show, we're going to provide a concrete example for how apps can be chained together through Parsl. So for example, we're going to have 3 steps in our workflow. We might have a simulation step. Oops, I'm sorry. There'll be a simulation step. That's the first bash app. And all it does is it's a wrapper for running an executable file that writes its outputs. There's a second step which will merge all the inputs and send it to the outputs. And that's also a bash app. It's got an executable called merge. It will take these inputs that are in one, and it'll merge everything and write it out to out to 0. Oh, I'm sorry, I keep missing the screen. Okay, the last app would be one of analyze, where the inputs from the previous step are going to be run through some kind of Python analysis package. And notice that this is a Python app and not a bash app, so there's no quotes in it to send it as a string. So it's just this last one is just Python code. So this is the stage where the apps are defined. What we have to do is we actually need to execute them. And so this would be the workflow code, where, so for example, the simulate simulate function has been decorated with the Parsl bash app. So it's not just a Python function. This thing is being interpreted by Parsl as something special, something to parallelize. And so by iterating over a loop, Parsl will see that multiple instances of it are being created. It will then send that job off for execution, but it will allow other jobs. It will allow multiple instances of that simulate function to be called. And the sims.append sims is just a list of the futures that are being returned by the simulation. So this is exactly what a weather forecast ensemble would do. Is it's going to run maybe 20, 80 different weather forecasts with slightly different initial conditions, and they're all going to ideally run in parallel at the same time. The next step is we need to analyze the data. And so here we would, for example, use the second bash app that we defined to merge all the inputs from, or all the outputs from the simulation. So that's, you'll notice that outputs here is being set to the inputs for the merge app. And then it is defining new outputs for its output. And so what it'll do is it'll first merge all the inputs, and then it'll send all those merged inputs. I'm sorry, it'll merge all the outputs. It'll send all those merged outputs as inputs to the analyze bash app, or I'm sorry, the analyze Python app. So that's the third step in the process. When we call this whole thing and we enforce the result, that's when we say we want all these futures to realize at this point. And so execution it'll work its way through, and then execution will wait until that final result is ready. Find this. Okay, great. So what we'll do in a few minutes is I'll show an actual example of code as it runs, and we can see and so a second approach may help clarify that as well. In the code, in the example that I run, there will be just a single app. A very important thing to note about Parsl is that it needs to be configured very carefully. Well, I mean, it needs a configuration in order to run on these resources. So, for example, if you were to run Parsl on a Slurm cluster, you would need to define this chain here would go. You have to set what Parsl calls an executor, and then you need to select the Slurm provider. Within the Slurm provider, you would input critical information about your Slurm cluster, like the partition or your username or the host where you would log into it. And you can also define things like the cores per node or the memory on the node, and whether or not you want it to be like exclusive use of that particular node. So these are all kind of classic things that would normally be defined with like srun commands. But here, Parsl includes that within a configuration that is loaded within Parsl right after it's been all set, right here at the bottom. And we also set storage access to basically say how to rsync files back to the starting point. So I've been mentioning, this would be a configuration for a Slurm cluster, sort of a traditional cluster. The other, for a cloud situation, Parsl can also be configured to run, for example, in this case, on Google Cloud. It would have a very similar kind of configuration, but there's different things in different places because Google Cloud calls things differently than what a Slurm cluster would. So for example, you would need, instead of a username and a login, you would provide a key file and a project ID. You need to tell it what region to run in. And for example, the instance type, this would be an N1 standard one. This would be a 1 CPU machine, a fairly small instance, but you can make that larger, a larger instance as well. And so similarly, all these things are loaded into the configuration, and then that configuration is then loaded into Parsl. So this tells Parsl effectively what kind of hardware to use. So what I'd like to do is show this with a live demo. Before I jump into code, though, I thought it'd be useful to have a process flow diagram so that you can see what we're about to do before we actually do it. I'm going to use an app called Ocean Parcels. It's for you. It's an oceanographic application used for calculating the particle trajectories based on ocean currents. So imagine something drifting in the sea, whether it's microplastics or whether it's a baby fish or whether it's potentially an oil spill. How does that move based on the movement of the currents? And we're going to jump to the ParallelWorks platform. There's a user container there where each user has their own files. They have an integrated development environment, and it's notebook aware. So right away, you'll be able to double click on a notebook file. The notebook pops up. And in that notebook, we're going to run some local tasks right there in the user container. But then we're gonna run some larger tasks that go out to the cloud workers. And those tasks are going to send a configuration and a launch information. So it'll be one kind of configuration, config one to one worker. It's going to run that configuration. It's going to run those particular particles that are assigned in that configuration. And then it's going to send over a different config file that has different particle starting locations to a different worker. So they're both doing different calculations, but they're using the same app to do the same calculation. And then when the workers are done, they're going to rsync their results back to the platform. And one key thing that I've already started the resources on this. So there are the two workers that we're going to use have already been spun up. And I've done that in advance because just to make the workflow run a little faster during the talk. And the other thing that is nice that the ParallelWorks platform provides is it will all the resource configurations that I just mentioned before. Those are stored in a very intuitive graphical user interface, and that's stored in a pw.conf file. So this is a resource configuration file, and that is sent. The notebook loads that instead of having to store all this information about the Parsl config that I showed in the two previous slides. So I'm going to jump to that. So there we go, switch tabs. All right. So this is the user container integrated development environment on the ParallelWorks platform. You'll notice it's displaying a Jupyter notebook in the center, and off to the side are the files that this user has access to. Everything that I do in this demo could also be done, say, from your laptop, but it would not have the ease of access and the same abstraction that you're about to see here. So I provided a preamble with kind of what we're doing. We've kind of gone over the key thing is we're going to start with some local calculations. And on the right-hand side, you'll see a couple files will pop up. These will be PNG files because it's making some plots. So we'll just run that. And so there it's running. And we'll see some PNG files created on the left side. And that's great. But unfortunately, my great science is it needs to run faster than that. So I can't just wait for these files to be generated this slowly. I'm going to break this whole calculation out into the cloud. And so here's where we're going to use Parsl to parallelize this process. You'll notice that I'm loading a config here. This is the same as the config as before, except this is the ParallelWorks configuration, but is in the same in spirit as the slides that I showed before. So I've loaded the configuration. I've now defined my bash app. So there's only one app in this workflow. And like the slides at the beginning of the talk, there's a config file that's being sent to the worker. That's saying which particles to launch where. There's the actual launcher file, and that is basically a Docker run statement. And then I'm telling it where to write to. So it's going to create an animated GIF file. And the run command is built up here, where the launcher, this is a Docker run statement. It's going to use Python as an interpreter, and the config is really a script that is being fed into the container to execute. This run command is the first item that gets put into the string, this string that gets executed as a bash, in a bash shell. And it will then make a directory locally, move the output into that directory, and because that, and then I'll show you in just a moment how it knows to rsync it back to the platform or to your local machine. So I'll run that cell, and now this is the workflow stage. So we've defined the bash app above, and run ocean parcels is the app we defined. That's right here. What I need to do is feed it the inputs, and I need to tell it what the inputs and outputs are. And so that's what I've done with these lines at the top. So what I'm doing is I'm telling it, I want you to use these two config files, test ocean parcels 1, test ocean parcels 2. I want you, for the launcher, I want you to use the wrap Docker script, which is basically a script that just says Docker run. And I'm specifying the out directory as this for this talk here. And each one of these things is fed into the path object, which basically returns the path of this file, whether it's on the local machine or whether it's on the remote cloud worker. So this is how Parsl can keep track of what you have of your path, where you are here, and your path on the cloud worker. And so what you'll see on the left side here is you'll see a couple log files being added to the actual workflow directory, and then up at the top we'll see these animated GIFs that are created by the workflow. They'll be put into the storage at the top. So let's run. And so all we're doing is we're looping over for each configuration in this list of configurations. We're running ocean parcels. It's sent that out to the workers. And it's just appending the futures, and execution is stopping and waiting right here where I'm calling for the result of these futures. You notice that it's little asterisk is still up here in this cell as it waits for those cloud workers to go. zoom window over so you can see when, oh, there we go. It's already sent its outputs into the folder and PyData Chicago. And so I have one output file from the first worker, an output file from the second worker. The files are it's a series of PNG files that have been squashed together into a single GIF. And the point here is it shows that config 1 was particles that have been launched all in the western part of the domain. The second config are particles that were launched in the eastern part of the domain. There are two different calculations that were run in different places. Of course, I could merge these results and make a single figure, but I'm showing them separately so that you can see they were indeed run in parallel and independent of each other. Another perspective, and so yeah, this is the southern tip of Africa with the Agulhas current that's moving particles around. With, you can see very, very strong red currents there with those big arrows, and then a lot of other turbulence around it. On the platform, I can keep track of the number of workers that I have access to. So this is a different tab since I don't want to disturb the image. Oh, and I'm going to change the zoom. There we go. This bar here tells me how many workers I have set up for this demo. I moved the sliders around to adjust the minimum and maximum workers. And so that everything would spin up quickly for today, I had the slider set all the way to 2. If I move it back to 0, it'll go through the worker auto shutdown sequence in a few minutes, or a minute or two. So this is a nice way to keep track of resources that are on or off. Since we finished our demo, I'm going to turn off the resource, and we'll go back to the talk. Okay. So the Ocean Parsl demo was a nice starting point because it goes through this process of defining an app as a Parsl app. It sends it the config and launch information. It runs it and it sends the results back. But now there's we've got more complicated things to do, and so let's take a look at another application that we've worked with. So here's an example from river or hydrology. We want to study we want to know how much what the respiration rate is in river ecosystems. So this is that respiration rate is how much food is converted to CO2 within the river, in particular within the sediment. And this is really important for 2 reasons. There's a climate impacts or generation of CO2. There's also, it's a good way to measure the net effect of the microbial activity in the sediment. And that can have really important impacts for thinking about pollution in rivers and whether the river is a healthy ecosystem. So there's sort of 2 ways to go about it, right? You can go to a river and you can get a flask of water and you can measure the production of CO2, the change in rate of CO2 per hour that's coming out of that flask. The other way, but those observations are very, very expensive and very difficult to maintain, or not, but they're very difficult to obtain. And so instead, what we'd really like to do is use a database of these measurements and train a machine learning model to predict what the respiration rate would be given the environmental metadata at that location. So at this stream, we know what its large scale characteristics are based on satellite data. So if we can train a machine learning model to predict respiration rate based on what the satellite says at that area, we can then make predictions of respiration rate at any other river that the satellite has seen. That's the general approach. Now, this is exciting. However, in addition, sorry about that. In addition to the fact that there's not tons and tons of data to work with, the really big challenges are that there's lots of machine learning models to choose from, and each machine learning model may have different hyperparameters that has to be fit in addition to the model parameters themselves. So what we've done is we've opted to use an approach where we just use every model we can find and optimize all of those models' hyperparameters. So schematic would look something like this. On the left column, or left side of the slide, is what would be an input data set. So it's like a CSV file, or like almost like a spreadsheet, where each row is an observation. Then each column would be a variable. There's the columns on the left side are going to be inputs to the machine learning. The columns on the right side would be the outputs. And so basically what we want to do is use the features, the left side of the data set, to predict the right side of the data set. And there's lots of different models that will be able to, that we can fit to this data to do that. And so instead of just selecting one, we use up to 14 of them. And each model may have its own hyperparameters. So we have to fit each model a certain number of times. We select the model with the best hyperparameters, and then we stack all those results together into a single prediction. So we have these 14 best models with their best hyperparameters, and we use all of their predictions, we stack them together to get a single result at the very end. And as you can see, this is a tremendous number of different actions that are all happening, and they need to be coordinated together in a workflow pattern. So what we did is this whole workflow is set up with a form at the beginning of it, so that it's fairly straightforward for users to run. So we would give it the input file. This is that row, that spreadsheet with rows and columns. We would tell it what the number of inputs would be. We give it a configuration file and whether or not it wanted to run this hyperparameter optimization or not. And over what it can do is it gets fit. It uses the environmental metadata that it has at each of these sites where we know the respiration rate, and it then is able to then predict respiration rate at other sites. And so we started with 180 data points, but we've made predictions at many, many other sites. You can see all across, well, this is just a zoom in on the continental US. We've also done it globally with other databases. And in the process, though, we learned that the scikit-learn, which is the framework we've used here, which is written in Python, we would expect it to have lent itself well to Parsl. But the pipeline objects within scikit-learn are very difficult to separate from each other. And so what we've had to do instead was use Parsl to launch the whole thing, but to launch the whole superlearner. But when it's running, it's actually running in parallel thanks to Dask orchestration or its own built-in parallelization. So what the lesson learned here is that sometimes the parallelization framework that's used is inextricably tied to the app. But just to note, I mentioned industrial design optimization, and this is an opportunity even though the internal aspects of the superlearner are going to be difficult to parallelize using Parsl, if the superlearner as a whole can be viewed as a single app, and then it can be then orchestrated within within a Parsl orchestrated workflow. So, for example, this would be an engine design optimization, a very simplified schematic of this optimization, where there are very expensive models to run a simulation within an engine. We'd use the superlearner to model that engine behavior to create what would be called like a surrogate model, or a much lighter weight model that behaves almost the same way as the big model, but it's just a machine learning model. And we can use that much lighter weight model to predict what the behavior of the machine learning model, or what the big model would be like over a very wide parameter sweep. And then we can go through and iterate the design process. And here, the superlearner could be deployed with Parsl if it's treated as a single app within itself. So I'd like to summarize with two other thoughts about the future. The first is that there's a lot of really recent and cool work to provide clusters in the cloud, in that the demonstrations that I provided today are basically one app or a series of apps being sent to individual and separate cloud workers. And that separation can be a barrier for really big applications that need to pass information back and forth to workers. So there's a new development where cloud providers are providing virtual clusters that are linked together. And ParallelWorks is working on optimizing these clusters so they have the same feel and performance as on-premise clusters. And then finally, the Parsl provides a tremendous flexibility in defining what resources you want to run. So on the left here is a config file from a Parsl, in Parsl, and you'll notice that there's two resources that are in here. Oh, I'm sorry. There's a Google Cloud provider, and down here there's a Slurm provider. And so if running with this Parsl configuration, your workflow, you can tell the Bash app decorators to use the cluster for a specific app, and you can use a different resource for a different app. And this would be great because it allows for mix and match and tuning of resources toward what they're running. So if you, for example, here, a weather forecast model might run a lot faster on a cluster, but then running the machine learning on that weather forecast model could be better done with a dedicated GPU instance in the cloud. So, so these are two interesting developments that are on the horizon. So with that, I'd be happy to take any questions you have, and thank you very much.
Thanks, Stefan. Does anyone have any questions? You can feel free to unmute yourselves. Okay, well, I won't keep us. Thank you so much, Stephen, for giving us this talk. Oh, Anna asks, any GPU implementations of this?
So yes, I have experimented with running a workflow on a non-GPU machine, going to GPU and back out. But so yeah, Parsl can run on a GPU, but it doesn't depend. I mean, it doesn't really matter. It's not like it's a specific implementation. There's no specific library for running Parsl from a GPU, I don't think.
Great. Any other questions? Okay. Well, thank you so much. Oh, I just have to keep ending this meeting. More questions. Sherry, if we use AWS as an executor, do I need to set up multiple EC2 instances?
So it depends entirely on what you need for your resources. So for example, if you want to use an instance that is small, you could have multiple instances all set up. If you prefer to so for example, if you want to use the free tier pricing, you could set up a whole bunch of T2 micros and they can work away. If you instead prefer to use a single large machine, then you have that choice in the configuration.
Great. So do we need, or is it preferred that we set up a ParallelWorks account to take advantage of the APIs?
This would be, well, you can use, Parsl is open source and available, we contribute to the Parsl project and use Parsl on the platform. So, but it's not required to use the ParallelWorks platform in order to use Parsl. Is that the API? The platform has an API associated with it where you can interact with resources defined on the platform via a platform API as well. But that's a different matter.
Sherry, if we set up on a local or single machine, is Parsl similar to the Python multiprocessing package?
That's a great question. I've not used the multiprocessing package, but I think my understanding is that it's going to have the additional benefit of being able to track how things go from one app to another. So Parsl will have more functionality in terms of keeping track of the app futures than a pure multiprocessing.
Okay, great. Well, I'm glad we had so many questions come through at the last minute. Yeah.
Thank you very much.
Yeah, thank you. We have these meetups monthly, usually the last Thursday of the month. So stay posted for our next meetup event. Thanks, everyone.
Thank you. Very interesting. Thanks a lot.
Thank you.